will share the screen. So today I wanted to have this, in fact, it's not a review session, it's a continuation of the lecture, but then I will have one or two problems. As I mentioned, tomorrow we have two presentations, we have a quiz, and then Monday and Tuesday I will conduct two general review sessions. Remember, I already sent the list of topics. So the topics like the propagation of waves in solids is not included. There will be no skin depth. Yeah, so there will be no Schrodinger's equation. Mostly it will be the density and yeah, so the propagation of electrons, electrical properties of metals, and the density of state for metals, the Fermi-Dirac distribution, and then semiconductors, intrinsic semiconductor, doping, PN junction. Okay, so this is really what will be the exam. So let's start. We talked about the semiconductor, intrinsic semiconductor. We talked about the P junction, the P type and N type, and now we started also the P junction, PN junction, and we mentioned this when we put a P type and N type close to each other. Remember, we have already calculated before the Fermi level of the P type and the Fermi level of the N type, and the number of holes in the P type is given by this function or expression, and the number of electrons is given by this in the N type is given by this. And when we put the P and N junction close to each other, obviously the electrons will migrate into the P type and the holes will migrate to the N type, and this will create an apparent potential difference and an apparent electric field. Okay, so this built-in potential, we can calculate it, and this will create a depletion region, because at a certain moment, the potential, remember, at a certain moment, because the electrons are moving from the N to P, and in addition to that, the electric field is increasing. This electric field is opposing to the motion of new electrons for N to P type, which means at a certain moment, there will be no electrons that can move and no holes that can move. And this will create a region free of charge. We call it a depletion region. Okay. So this the built-in potential is equal, if we want to calculate it, the potential energy due to this depletion region is equal to the difference of the Fermi-Dirac levels N minus the Fermi level P. We can also calculate, we have already calculated before, the Fermi level in P type and the Fermi level in N type, and then we can calculate easily the potential, the built-in potential. The built-in potential, as I mentioned, is EFN minus EFP, and then we can easily see that the built-in potential is equal to the KT Boltzmann constant temperature divided by the electric charge, and then the logarithm of the number of donors, number of acceptors divided by the intrinsic carrier density squared, of course. So here we gave an example, and you can see, we can easily calculate the potential difference. This is the built-in potential when you put a P and N junction with these acceptors and donors level. Okay, so then we went and started looking at what happens at this depletion region. So we are interested to look at the electric field, okay, in this depletion region, and at the charge density in this depletion region, etc. As I mentioned, the charge density, the PN junction creates a depletion region that has a negative side or negative polarity in the P side and the positive polarity in the N side. This is very important. Now we can easily do some Maxwell's equations, and the gradient of the electric flux density is equal to the charge density, which means we can easily see that the gradient of the electric field is equal to the charge density divided by the permittivity of free space, of its permittivity of the material. Okay, so here, remember we have two sides. We have the N side, P side, sorry, and we have the N side. So the charge density is different. Now the charge density is the number of charges divided by the charge of one charge, which is E, the charge of the electron, and then obviously we can divide by epsilon. So in the region, so here is something that I just want to remind you. The depletion region has, we always take 0. This is the 0 of the depletion region. This is the 0. The origin of the depletion region is exactly the interface between the P and N. The width of the depletion region goes from minus xp, a parameter, that xp, which is a negative, it has a negative sign because it's a negative x, to xn. This is the depletion region. So depletion region goes from minus xp to xn. Sorry, xn. Okay, remember the width of the depletion region will be xp plus xn. Okay, this is the width of the depletion region, which we will talk about it later. Now we want to look at the charge density. What is the charge density? Means the number of charges per unit volume. Now in this area, the number of charges are the number of acceptors, because each electron will go to a hole. So the number of acceptors. So in this area, in this region, from minus xp to 0, minus xp to 0, the charge density is equal to minus the q and a. Okay, because we have a number of acceptors per cubic centimeters. Okay, times the charge of the one electron hole. Who can tell me why there is a negative sign here? Why do we have a negative sign? Can you hear me? Okay.
Yes, we can hear you.
Okay. Okay. Yeah, no, not from minus xp. I'm talking about why I put a negative sign here. Now I know Amna, yes, Amna is right. Yeah, so the charge of the electron is negative. Yes, Fatma. Yes, in fact, because in this side, remember, I have the electrons that are populating this area, right? So that's why the charge density is a negative. Okay? Is this clear? So this negative side sign comes from the fact that the electrons are populated here, because they migrate from the N to the P type. So this is the charge density in the P side, and which means the electric field, the gradient of the electric field, is equal to minus Q NA divided by epsilon. Similarly, the charge density in the P type from 0 to xn is equal to QND, Why it is positive here? Because here we have a positive charges that are accumulating in an n-type. Okay, is this clear? So this means that the charge, the gradient of the electric field is equal to the charge of the electron, well, the absolute charge of the electron, the number of the donors divided by epsilon. Now we would like to look at the following. We would like to look at the electric field. We want to calculate the electric field. Okay, so let me start another. This is what we want. We want to calculate the electric field. So those are typical exam questions, please. So please pay attention. Let's start from the following. I know that this is the PN junction. This is 0. This is minus XP. And this is XN. Now, in general, XP is different than XN. We will see why. In general, XP is, so this is the width of the depletion region. Okay, so now I want to calculate EX. This is what I want. I know that the electric field is equal to the following. We just, no, sorry, the dielectric field, the gradient, let's say, take one. The gradient of the electric field is equal to minus QNA over epsilon when X is between and 0, and it is equal to QND over epsilon when X is between 0 and X. So what do I have to do? All what I have to do is to integrate. Now let's take region 1, region between minus XP, X and 0. So EX will be equal to the integral of minus QNA over epsilon, which will give me minus QNA over epsilon X plus a constant, right? Do you agree? I just calculated this X. Now I want to calculate the constant. The constant, I want to calculate it using the boundary conditions. I know at X is equal minus XP, what will be the value of the electric field? What will be the value of the electric field here? Hello? Okay, I have one good answer. Okay, please. No, the value, I'm not talking about the sign. I'm talking about the value. Let me do it here to clarify my question. I just want to open a window here. I have, this is my PN junction. Please follow. This is my P and N type. And I have an accumulation and negative charges here and positive charges here. And here there is nothing. There is nothing. So the electric field is only here. So which means the electric field here is 0. So the electric field is 0. And the electric field here is 0. Do you understand? Because here there is no potential difference. No, the electric field will be equal to 0 at this point. Do you understand? So the electric field at minus XP is equal to 0. Let's put it in this equation. This means minus QNA over epsilon times minus XP, because I replace X by minus XP, plus constant must be equal to 0, which means a constant is equal to minus QNA over epsilon. Now I replace in the original value. This means that the electric field is equal to minus QNA over epsilon x plus xp when x is between minus xp and 0. This is a very important quantity. Are you following? Hello? Is this clear for you? Okay. Now we want to go to the other region. Remember, I did this region 1, and I want to go to region 2. So now the region between 0 and x and xn. I know that the electric field, the derivative of the electric field, this is what we did here. The derivative of the electric field is QND over epsilon. Is QND over epsilon. Again, we do the same thing. This means that the electric field is equal to the integral over epsilon dx, which is equal to QND over epsilon x plus constant. Now, boundary conditions at x equal xn. What will be the electric field at xn? Xn is here. This is xn. What will be the electric field? The electric field will be
0.
0. Okay, so the electric field will be 0. I replace, this means that QND over epsilon xn plus constant is equal to 0. This means the constant will be equal to minus QND over epsilon xn. So now I go back and I write the equation of the electric field, which is QND over epsilon x minus xn, and this is when x is between 0 and xn. So what we just did, we just calculated the expression of the electric field in the depletion region when we go from minus xp to xn. Is this clear? Okay, I have a question. Let me choose another color here. Okay. At x equals 0, what is the electric field? At x equals 0. What is x equals 0? X equals 0 is the interface, is this. This is x equals 0. Is the interface between the P and N type, which is the real interface of the junction. So how do we calculate E0? All what we have to do is to, hello, no, they don't know. The electric field is a continuous it's a continuous function. The electric field, okay, let me just do this again. I have, this is x, this is 0, this is x, this is xn, this is minus xp. I have the electric field. I have the electric field that starts from here. This is electric field given by let's say I will call it E negative X, which means the negative one, the blue one, this one. And there is also another expression that goes from here, which is a positive one, the red one. They must be equal. They must be equal. Do you agree? The electric field is a continuous function. This must be equal in the interface. So the electric field at zero, if we take the blue part, it will give me, if I replace x by 0, it gives me minus QNA over epsilon p, minus QNA over epsilon xp. And it is also equal to QND over epsilon minus xn, because if I replace by 0, it gives me minus xn. And this must be equal. So this means it gives me a very interesting equation, which is QNA over epsilon is equal to QND over epsilon xn. Here it why? Okay. QNE over this is XP is equal to this. I can replace do this, and this will give me a very, very interesting fundamental equation in the PN junction. That is the number of acceptors times the width of the depletion region from the P side is equal to the number of donors times the width of the depletion region from the N side. This is a very important equation, and this is what we call the charge conservation equation. Charge conservation equation. Okay, this is the charge conservation equation. Are you following? Okay. Then, by the way, this is very fundamental. Many times you will be asked, for example, to say, okay, what is the ratio? What is the ratio? Xn over xp, for example. Well, xn over xp is equal to Na over Nd. Okay, so the number of acceptors in the p-type divided by the number of donors in the n-type. Okay, it's very, very interesting as equation. Okay, so now let's add another page and see another question. Let me just write the equations again. The electric field is equal to minus QNA x plus xp when minus xp is between x and 0, and E is equal QND over epsilon x minus xn between 0 and xn. Okay, and we have seen that NAXP is equal to NDXN. And obviously, the width of the depletion region is equal to NX as XP. Okay, so these are very fundamental equations. Now, I wanted to calculate the how can I calculate the potential? The potential. How can I calculate the built-in potential? The built-in potential, I can calculate it if I have the electric field. Okay, now I have a question for. I did not understand your question. This is only at x equals 0.
The charge conservation equation.
No, the charge conservation equation, we got it at x equals 0. But it is everywhere in the PN junction.
Okay.
So we were able to calculate this because the electric field is the same at x equals 0. But when we do the electric field equals 0, at x, the electric field is equal at x equals 0, we end up by this fundamental equation, and this relation holds for any PN junction, regardless of the position where you are looking for.
Okay, thank you.
Okay. Now, if I have, again, I have the following, as I mentioned, I have a PN junction here, and this PN junction created a negative potential here and a positive potential here, which means I have an electric field here, right? This is an electric field, and this is a built-in potential. Well, I just calculated the electric field here. Okay, this is the expression of the electric field here. Okay, I want to derive an expression of the potential, built-in potential. How can I do this? If I give you the expression of the electric field and I ask you the expression of the potential, built-in potential.
Isn't V equals E times D? Electric field times the length of the semiconductor, maybe?
Okay, but this is when you have a constant electric field. Here we don't have a constant electric field. Okay, if you try to draw, okay, so this is a very important thing that what you said, Isa. Let me again explain this to you, because I really want, from the electrical engineering point of view, I wanted to make it sure. So you are referring at the, let's say this is a positive and this is a negative, right? Capacitance in the capacitor, and you have an electric field, right? And you have a D, right? And you have a potential difference delta V, right? And you are saying that E is equal delta V over D, right? This is what you are saying.
Yes.
But this is a constant electric field. This is a constant electric field. Remember, the V, or the potential, is always equal to the integral of the electric field. In this case of the potential of the capacitance, the electric field is constant. That's why the potential difference, we can omit for the moment positive. That's why the E is constant, so it becomes ED. Did you see the problem?
Yes.
Here, no. Here we just developed, what is it? Yeah, we just saw that the electric field depends on X, which means the electric field will change as a function of X. In fact, if you want to draw the electric field, I mean, you can see, you can draw it. This is 0, this is minus XP, and this is XN, and this is X. You will see that the electric field do this something like that. So the electric field, this is the electric field. You can easily see, compute it. The electric field will go linearly, and then will go down linearly. Okay, so this is you cannot do this direct relationship. So you have to integrate. You have to integrate E. Do you agree? Do you see the problem?
Yes.
Okay. No, but yes, you are right, except that
in this case, the electric field is not constant, so we have to integrate. Now, the problem here is, well, we have two electric fields, right? So I have to integrate from minus xp to 0, okay, the electric field, which is this one, okay, I have to use this one, plus the integral from 0 to xn of ex, of course, dx here, which is now this one. So we have to integrate. Now, I mean, it's easy to integrate. Okay, it's very easy, of course, to integrate. I will not do it. It could be as a kind of just exercise for you, but you can easily see. Well, let's do only this one. Let's do only this one so that those who probably have some issues, we can help them. So I want to integrate this first part. Let's say first part. Let's do it very quickly. So I want to integrate from minus xp to 0 of what? Of ex. Ex here is minus qna over epsilon x. So minus qna over epsilon x plus xp dx, right? So it will be minus qne over epsilon, and then x becomes 1/2 x squared, and xp becomes xp x from minus xp to 0. So if I replace, it will give me minus qna over epsilon. Well, 0, it gives me 0, of course, because I have the x here and x here, minus 1/2 xp squared, and then minus, which is plus xp squared. Okay, and this gives me minus qna over epsilon. Xp squared minus half xp squared, it gives you 1/2 xp squared. Okay, and then it will give me minus qna over epsilon times 1/2 xp squared. I already see a question here. Okay, I see a question. Let me explain what I did. Let me just focus on this one, on the one in blue. This one, right? This is the question of Amna. So Amna, so I have 1/2 x squared plus xp x between 0 and minus xp, right? So what I do this of 0 minus this of x minus xp, right? Exactly. Yeah. So that let me just explain it so that people don't confuse. So Amna, very good, you understood it. So this will give me 0 because x0, this will make 0. Minus, I will keep minus here, and I will just explain here. So this will give me 1 xp squared, and then minus xp squared, right? So if I introduce minus, this will give minus, and this gives positive. That's why I put positive here and negative here. Okay. Okay. Is this clear for everyone?
Yes, that makes sense.
Okay. The same thing, you can do exactly the same thing from the, this is, so we did 1, you can do 2. So I will say here 2 to be done at home. To be done at home. Okay. It's just a normal integral. And then you will obtain the famous VF, the built-in potential, which will be 1/2, and then E0 square, E0, the absolute value, and times XP plus XN. Now, you will see that it's, what is E0? The absolute value of E0. Absolute value of E0, if when you replace X by 0 here, so it will be QNA over epsilon. It will be QNA over epsilon. It's also QND over epsilon. This is X equals 0. epsilon xp, and this is xn. Are you following? So this is, if you do VF, you integrate VF, part 1, we did it together, part 2, and then you add them together, and you will see that you can get this expression, which is a very important expression. Okay. You can also, which other formula? This one? This one, right? So you mean this ones? Hind? Yes, obviously. Yes, obviously. E0, as I mentioned, E0 will be, that's why E0 is, it's either this one or this one. Both of them are equal. You can use E0 here, so it's not a problem. Obviously, I can calculate, we are interested to calculate the width of the junction. What is the width of the junction? What is the width of the junction? Exactly, xp plus xn. So the width of the junction is xp plus xn. So xp plus xn. So xp plus xn will be equal to, we can easily see that this to be, you can prove it. It's equal to epsilon over q, and then 1 over NA plus 1 over ND, no, E0. Okay, this is the width of the junction. Okay. Any question? Do you know how we got this? Think about it. Well, you have everything, in fact. You have everything. Okay, we know that from this equation, what is XP? From this equation, XP is equal to epsilon E0, absolute value, divided by Q and A, right? Okay, and the same thing, Xn is epsilon E0 divided by Q and D. So XP plus X and D will be E0 in common, epsilon over Q in common, 1 over N plus 1 over ND. Okay, is this clear? Hello?
Yes, it's clear.
So now I can also, you can play a lot about this. I can also replace this here, include this here. So this will give me VF, another formula for VF, which is 1/2. Now, instead of having E0, I want to replace E0 by its value and XP plus XN by its value. All what I did, I replace E0 and XP and XN by them value. E0. I replaced E0, I will get this squared Q over epsilon and then NA ND over NA plus NT. This is another formula for the built-in potential. Okay. Obviously, what is this? This is the width. So this means that the width of the PN junction, which is one of the most important things in the PN junction, the width of the PN junction can easily be extracted from here, isolated, and this will give me 2 epsilon over Q, the built-in potential, and then NA plus ND over NA times ND, and everything to the power of 1/2. All what I did, I just isolated this one. Okay. We know, remember, we already calculated that the built-in potential is equal to the Boltzmann constant, the temperature, divided by the charge of the electron, and ln of Na ND over the intrinsic carrier density. So you can easily also include this here. So you have to play with these parameters. Okay. Now, what did I calculate for the PN junction? I just want to summarize so that you don't lose track. For the PN junction, we calculated the depletion region. Of course, for the PN junction, you will have an A, the number of acceptors in the P side, and the number of donors in the P type. This is what you will be given, for example. Okay, you will be given 2 silicon semiconductors. Those semiconductors, one of them is P with Na, and one of them is N with Nd, and they will be put together. And the question will be, what is the built-in potential? What is the electric field? For example, what is the electric field at 0? What is the XP, the depth of the P side? What is the depth of the N side? Okay, and what is the width, which is equal xn plus xp? This is basically what you will be asked. The rest is just calculation. There is one thing else. Now I want to go back to what I was mentioning to Isa. Now you have a potential difference here. You have a potential difference. This is the, well, let me give the width. This is the width of the PN junction. You have a width, you have a potential difference, right? If you have a width and you have a potential difference, you have here negative side, you have here positive side. Well, this means this one is acting like a capacitor, right? Because in the capacitor, you can also have a non-uniform electric field, for example, if you have several dielectrics. So if you have a capacitor, this means that you need to calculate the capacitance. This is an important quantity in the PN junction. What is the capacitance of the depletion region? And the capacitance, who can tell me what is the capacitance?
Q over V.
It's not epsilon over the width. Do you remember this? So the capacitance, you can also calculate the capacitance, which is epsilon over the width. This is physics 2. So let me just, we will do some examples. Those are the most important parameters that I want you to. So most of the time, those parameters you will be asked to calculate. I might ask you to demonstrate the electric field expression, those 2 ones. This one. Okay. Okay. So let me go for an example. I think I have an example here. Can you see?
Yes.
Okay. Okay. So now you are given a number of donors. This is a very straightforward, by the way. So the number of donors, number of acceptors, and the intrinsic carrier density. So calculate the expression or the ratio xn over xp. Well, xn over xp, we already saw that from where we can get it.
From the charge conservation equation.
Exactly. So the charge conservation equation gives me that the number of acceptors times the width of the p side is equal. Remember, it's the width of the p side of the depletion region. It's not the p side, the whole entire p side. It's just the depletion region is equal to the number of donors times xn. So we are asking about xn over xp, which means na over nd. Now remember here in this equation, for example, in this exercise, it is in cubic centimeters. So the number of acceptors is 10 to the power 14, and then 10 to the power what is no the number, yeah, 10 to the power 18, yeah. Okay, and so this will give you yeah, I'm just thinking, so this is meters, okay? In fact, because the formula here in meters, okay? In fact, even you should calculate, you should convert it to
Professor, shouldn't be in centimeters because didn't change the units yet.
okay, that's a good question. That's a good question. No.
There shouldn't be units because it's a
Yeah,
ratio.
yeah. In fact, I'm thinking about okay, thank you very much. I think you are more focused than me now. Let me see. In fact, I was thinking about something else. In fact, I was thinking about, in fact, it is always better to convert everything to meters. For those who will view or look at their copies of midterm 2, I see a good number of you still struggling with not only the conversion, but sometimes, well, you do the whole analysis in cubic centimeter, for example, and then you give the result in cubic meters, which is I think some of you, they still don't realize. If I give you, for example, in this case, the intrinsic carrier density or concentration is in cubic centimeters. Now, unless there is a reason, you should, and in addition to that, the mobility in the exam, I give you all the mobilities in centimeters minus 1. Unless there is a big reason why you want to convert everything and to do a mistake. Because at the end, you could calculate because I asked in one of the questions the conductivity. Well, you can give me the conductivity in centimeters minus 1. Okay, so now I was thinking about it. Yeah. So yes, here the 10 to the minus 4, it's the depletion region, the ratio of the depletion region. Yeah, calculate the depletion layer width. So how do you calculate the width of the depletion region?
xn plus xp.
Yeah, okay, xn plus xp. And then okay, so you don't have xp, you don't have xn. You have a ratio between them. Now, you could isolate you have the ratio, you can isolate. But yeah, any question, any idea? At least any okay, so
Should we get it in terms of one of them?
no, you have to take it's a calculate. You have to calculate. Anyway, think about it. It's a very simple question. Think about it. I want to move to the other question because we only have the other question. We only have 5 minutes. But yes, you can calculate it from. Obviously, don't forget that you have also the electric field at the origin, and you have other parameters in the built-in potential, etc. that depends exclusively. Remember, the built-in potential depends exclusively in the number of okay, right? And if you calculate the built-in potential, you can easily calculate the width. Remember that the width is 2 epsilon over Q VF, and then NA plus ND over NA ND, and then everything of 1/2. So you have this epsilon, it's given, it will be given. VF you calculate it from here, and NA ND you have all of them, right? Hello? Are you following? Did you understand what I said?
Yes.
Yeah, so the here you cannot have, because you have only one equation with 2 unknowns. Yes, 2 times epsilon. Yeah, we just did this equation. We did it just here. Yeah, so this is yes, here 2 epsilon over Q. So the question was the width. So the width is equal to 2 epsilon over Q, the built-in potential, NA plus ND over NA ND. You cannot calculate XP and XN because you only have one data and you have 2 unknowns, XP and XN. It's impossible. So you have to calculate VF. You have the room temperature, you have Boltzmann constant, you have NA, ND, and you have intrinsic carrier density. Once you do this, then you calculate the width. Okay. This is also a typical question. I will not solve it, but this is, I wanted to, yeah, you can take a screenshot or I will post it tonight. But this is a typical question that we can solve in the review session. Now, the first part, I want to talk about it because this is the first part that I gave in the exam. So, for example, for one of the questions was, a silicon is doped with arsenic with the doping ratio of 1/18. As I told you, the doping ratio means that in this case, we have arsenic, which means the number of donors is equal to the number of atomic concentration, which is, I gave it, divided by 10 to the power of 8. It will give you the number of donors. Okay, calculate the doping concentration and the conductivity. Well, this is the doping concentration, and the conductivity, it's easy. The conductivity is mu E and then NT, and then you get everything. Calculate the number of minority charge. Here, many students, they still are struggling with the minority and the majority charge carrier densities. So this is the doping for N-type. This means the major carrier charges are electrons. So the minority will be holes. Okay. And how do you calculate the holes? You know that the number of donors times the number of holes is equal to Ni squared. You have Ni, you have Nd, you can get Nh. Okay. So this could be a problem. And of course, calculate the total conductivity semiconductor. Then this is an N-type. The following question, to make the link with what we just saw, the semiconductor is put in contact with another semiconductor material that has a hole doping with a ratio of 1/10⁹. So now I am putting a p-type and n-type. So the p-type has, what is this, 5×10⁻14. This is nd, and this is Na. Na is 5 divided by 10⁻9 is 5×10⁻13. So we have Na, we have Nd. Again, calculate the width of the depletion region. Very straightforward. We just, I mean, here in principle, this question should come before calculate the built-in potential. You calculate the built-in potential, you have everything. You have the Boltzmann constant, temperature, the charge of the electron, the number of acceptors, the number of donors, and the number of the concentrate, the intrinsic carrier density. So you can calculate it. Calculate the width of the depletion region. Calculate the capacitance of the depletion region. And then calculate the electric field exactly at the barrier of the PN junction. Here means E0. So I will do similar problems, but I just want to do this. There is one thing that it will need some 10 minutes or 15 minutes or 20 minutes. I will do it in the review session on Monday. Remember, do you have a question before I go to just 1 minute to it to in fact explain to you something else? Yes, E0, you need to prove it. Yeah. I might give you the formula if you don't need to. I still need to think, but I might give you the formula of the electric field, or I might ask you to calculate the electric field, to derive the expression of the electric field. Now, let me just show you what I will do in the review session. The 15 minutes that is left. This is the width of the PN junction, all right? We have electrons here, we have positive charges here. So the width of the depletion region, we have a built-in potential, etc. Now, what will happen if I apply an external potential difference, V external? What happens if I apply external potential in the forward bias mode, like the one we did with the Schottky, or in the reverse bias? So what happens to XP, Xn, the width, the capacitance, and the electric field of the depletion region? This is what is remaining. Because remember, the PN junction is used in electric circuit with external potential difference. Okay. I will stop here. So let me tomorrow, as so tomorrow I will give you a quiz. The quiz will be in person. We will be in the room, and it will be in group of 2 or maximum 3. Okay. So thank you, and see you tomorrow, inshallah.
Okay, Professor.
Yes, I will upload it today. Yeah. Yes. Yes.
For example, let's say my grades are full mark in the previous quizzes and all quizzes. So will, like, if I get a bad score in this quiz, will that drop my quizzes off, or?
Okay, so wait.
Off? Because I'm not getting.
Okay, so the what I will do, I will remove the bad quiz for everyone.
So you will drop the lowest quiz, right?
The lowest grade.
Okay, thank you, doctor.
You're welcome. Okay. The quiz will be So no, it will not cover what we have seen today. It will cover the PN junction. It will cover the built-in junction because we have seen it before, but it will not cover the width, the XP, XN electric field. Okay, so the makeup quiz, I know that there are two problems here, and that's why it creates a burden. There are some people who miss the quiz and miss one exam. Please send me an email about your availability Monday and Tuesday, because I need to do it. Yes, I graded the exam now. I am grading the quiz that we will that you did before. So inshallah tomorrow you will get it.
So how
Yes,
about our grades in the presentation?
I will give the grade of the presentation after the last two presentation tomorrow, inshallah. But I know the grades. Okay, I know the grades. Okay, have a nice day. Bye bye. Tomorrow, see
Thank
you
you.
tomorrow, inshallah.